Hello, this is Adrian Galdran. I'm going to present you our work on the segmentation of diabetic foot ulcer images. This is joint work with Gustavo Carneiro, MICCAI, Ballester. You can find the PDF in this archive link, and then also the code to reproduce our results in this GitHub link. Now, if you open a generic computer vision image segmentation paper, you will find out data sets that all have lots of categories, and actually they are each class in a picture that appears in a picture. It tends to appear relatively in a well-balanced manner, like each category is well represented. It's not the case for medical imaging. You all know that when you are dealing with lesion segmentation, which is a binary segmentation problem, lesions tend to be quite small. And also the second category is the background, which contains everything that's not a lesion. Therefore, it contains like lots of things, and it's typically the background overwhelms the lesion in terms of region size. So for this reason, I believe people in computer vision tend to use more the cross-entropy loss, and then in medical imaging we use alternatives, as we will see in a moment. So just some notation, we are going to refer to the segmentation when it has values between 0 and 1, a soft segmentation as y hat. Okay, and then from y hat you can generate a binary segmentation y bar by just simple thresholding, for example. Okay, and then there's also y, which is the ground truth image, and both y bar and y have binary 0 or 1 values at each pixel. Now this is the formula for the cross-entropy loss. You will see here there's this indicator function, which means this takes a value of 1 whenever the ground truth image belongs to class C in that pixel, and 0 otherwise, which means that the loss function only takes a value different than 0 for pixels that belong to class C in that case. Now if you can rewrite this for the binary case in which the probability of background is 1 minus the probability of foreground and vice versa. So you can use that fact to reformulate the cross-entropy loss as a BCE, binary cross-entropy loss, which has this formula. Now for medical image segmentation, as I said before, there's this DICE score. Actually, this is the DICE similarity score. It's not the loss function, but the metric. Okay, it's an overlap metric. It becomes 1 when your binary segmentation y bar is the same as the ground truth image y. Otherwise, the value of the DICE similarity score decreases, and it's computed by using this formula, which has the intersection of both things in the numerator and the union more or less in the denominator. You can actually draw quickly a picture and realize that this is true positives in the numerator, and then in the denominator you have true positives, false positives, and false negatives, which actually goes to show you that the DICE similarity coefficient does not care at all about the true negatives, which are pixels in the background that your model predicts correctly as background, which are kind of trivial pixels. So this is nice for class imbalance. You can also rewrite this if you want to use this with your soft segmentation with values in between 0 and 1. You can generalize this by just realizing of these two identities with the scalar product involved. You can just take a moment to understand that this is correct, and then with that you can rewrite the DICE similarity coefficient as a score, as a loss function for training your models, but just you invert it because you want to minimize it in this case, and then this you can use with real values instead of binary values, and you can use it for backpropagation and gradients and all this stuff. Now, while these are two very popular losses that we already know from the literature that the binary cross-entropy loss has better calibration than the DICE loss, but the DICE loss works better for imbalanced scenarios. So what we don't know is what is the best way to combine them. Okay, it's very popular to just simply add them, but there's other alternatives. We are going to study 5 of those alternatives in this paper, in this work. So first there's the just minimizing the cross-entropy loss. Then there's adding them, which is very popular, as I said. We also use this soft fine-tuning strategy, which means that you just linearly interpolate from the beginning of the training, which you use only BCE, and then by the end of the training you are just using only DICE, and in the middle you just interpolate the value of those two losses for the minimization. Then there's the hard fine-tuning, in which you just take 90% of the training time. The first part of training you use the BCE, and then in the end of training you switch to the DICE loss. And finally, just using the soft dice loss for training. So we want to understand the impact of the choice of these loss functions in our problem, in the lesion segmentation problem, and also we want to analyze the behavior of these losses in the particular case when we have out of distribution data. So this is a bit of a complicated matter that deserves some little discussion. So in classification problems in machine learning, you can find lots of papers dealing with out of distribution detection. And usually in some papers they call that the situation where you have data in training time that belongs to a set of categories, and then in test time you receive an example that comes from a different category. So that they call it out of distribution sample. Okay. What you want to do with that sample, with that example, is you want to reject it. You don't want to classify it because you don't know how. Okay. And this is OOD detection. On the other hand, there's some other papers in which they call OOD data to a different thing. They call OOD data to data that belongs to the same categories as you saw in training, but has a different nature, a different aspect. Like the distribution has shifted, and now maybe you can think of a brain scan that you took in one hospital, and then the same person goes to a different hospital, and it takes a scan with the different machine, and it looks different. Okay, maybe a different kind of a scanner or whatever. So what you want to do with that data is you want your model to process it and segment it or classify it correctly, and then your model will be generalizing, and you will call your model robust to OOD. Right. In this case, we are dealing with lesion segmentation, in which we have, for training, we use images that always have a lesion. Okay. So what happens if the model in test time can also receive images with no lesion? Is this OOD? We believe it is in a subtle manner. So your model has seen lots of pixels that are background, so this is not at all OOD at the pixel level, so background pixels are fine, but at the image level it is OOD, and you want your model to be robust, because your model has not seen images without lesions, which means that is not used to it, and your model will probably underperform. In this case, you want your model to segment a black image when it's no lesion, there's no lesion there, and that's your model being robust to this OOD situation. So let me just go directly to results, so you can check the training details in the paper. Okay, but this is for the foot ulcer segmentation problem. You can see that this is the kind of images we have. 2000 for training, and then 2000 for validation, and 1800 for test, and we did not have the ground truth for the validation and test images, but we knew that some of them would not contain foot ulcers. So the validation and the tested contains some images with no lesions. In order to assess performance, we just train 5 models in a 5-fold manner, and then average the dice score, the dice similarity coefficient. And this is the in-distribution performance, because we know that there's always a lesion in the training images. Now, for the OOD performance, we submit to the grand challenge an ensemble of the 5 models, and they return to us the average dice score for all the images in the validation set. Okay? Now, they also said that the dice score would be 0 for false positives, which means that you say there's a lesion when the image contains no lesion. And then the dice score will be 1 if you say there's no lesion and actually there's no lesion. Okay, so this is the in-distribution performance for the challenge. As I said, a 5-fold cross-validation average dice coefficient, and we can see already that the addition of BCE and DICE is kind of the best. By the way, this is all the architectures we tried, like a lot of them, from the very small MobileNet and ResNet 18 to the very large ResNet 152. Okay, so the BCE+Dice is a very good choice for when your images are in distribution, when you only have images that contain lesions. And also the soft fine-tuning, which starts by BCE and then interpolates between BCE and DICE. This is also a very, very nice choice. And by the way, the other ones are quite far away in performance, although the DICE loss is quite comparable. Now, what happens when you go to the out of distribution validation set that contains images with no lesions? Everything changes. Like, it turns out that the best thing to do in this case is to use actually the hard fine tuning, BCE, and then when you arrive to the 90% epochs you switch to DICE, or the BCE loss. So forget about DICE, and then also forget about the addition of DICE and BCE. those are not very good ideas when dealing with auto-distribution, no lesion images. Then in order to verify that this is actually a general claim, it's not only for this dataset, we also used a second dataset for polyp segmentation. So we took the Endotech 2021 benchmark that contains 1000 training images, all of them with polyps, and then a test set with 200 polyps. Okay? Now, in order to have auto-distribution data in the sense that we are talking of here, we also added 20 ulcerative colitis images. So this is going to be our OOD data because these are images without polyps. For the performance is measured in the same way, and the results are, well, there's better performance because this is an easier problem, easier dataset, but the conclusions seem to be similar actually. So for in-distribution images that only contain polyps, again, the addition of BCE and DICE seems to be a very nice idea, a very nice loss function to minimize to train your models. And then if not, you can also use the soft fine-tuning linearly interpolated loss functions that go from BCE to DICE. Okay. However, if your test data is going to have images that do not contain polyps, then in that case, again, it's a good idea to use just the binary cross-entropy loss or the hard fine-tuning approach in which you only switch to the DICE loss in the end. So just for concluding this presentation, it's known that the BCE and the DICE score losses are good for in-distribution segmentation, but the behavior of combinations of these loss functions has not been so much explored in the literature, so we wanted to do that for lesion segmentation. We saw that when there's OOD data, then BCE plus DICE, which is very popular in competitions, might not be the best choice because there's not so much robustness here. In this case, it would be best to use the hard fine-tuning approach or even the standard binary cross-entropy loss. Note, however, that the hard fine-tuning approach requires you to set a hyperparameter, which is the number of epochs you train before switching to the DICE loss. Actually, this is not correct. It should say number of epochs before you switch to the DICE loss. And finally, I will correct that in the final version of the slides. And finally, we were expecting much more from the DICE loss alone. I mean, I know it's known that it's not well calibrated, so when you do not have lesions, it's going to be not so good. But since we are doing heavy model ensembling, like we are using 5-fold training, so we are training 5 models, and it's known that ensembling models improves calibration. We were expecting the DICE loss to be a bit better, and actually it's very bad. So whenever you suspect there's OOD data in your test set, please do not train your models with the DICE loss. This is the take-home message. Okay? Thank you very much, and thanks for watching my talk, and see you around.